I would like to welcome you to virtual conference on chemistry and its application with the theme Transforming Chemistry and Interdisciplinary Research to Innovation. I would like to use this opportunity to thank the organizing committee for the effort in organizing this prestigious conference. My name is Dr. Umar. On behalf of my colleagues, Dr. Sahar Abdullah and Dr. El Asani Al-Noor, I will be presenting our research work titled Effect of the Position of Hydroxyl Functional Groups on the Structural, Spectroscopic, Electronic Properties, and Antioxidant Activities of flavones and flavonols using density functional theory method and molecular docking investigation. My presentation will be based on the following outline. I will briefly give the background of our research work, the molecules that are used in this research work, which we call the targeted molecules. This will be followed by computational methods that are employed in this research work, and then some of the results will be presented and discussed, which will then be followed by conclusion. Flavone is an organic compound that contains 3 rings, 2 of which are aromatic rings, which we label as A and B, and the aromatic ring is also attached to a heterocyclic pyranone ring, which we label as C. This in general, this compound in general contains 14 carbon skeleton, which consists of 2 phenyl ring A and B, and then heterocyclic pyranone ring, which is labeled as C. This compound is of little or no practical application, but its substituted derivatives such as flavones, flavonols, flavonoids are a large class of nutritionally important natural compounds that are used in so many applications. Now, if once the hydrogen of the flavonone is replaced with hydroxyl group, then it is called, the compound is called flavonol. So flavonols are flavones that have hydroxyl group at position 3. So these studies involve 4 different flavones and 2 different flavonols. The targeted molecules are 6 molecules, which are tetrahydroxyl flavones, which means that they contain 4 hydroxyl groups attached to flavone backbone, but these hydroxyl groups are placed at different positions, and therefore they are called positional isomers. For example, ficetine has hydroxyl group at position 3, position 7, position 3 prime, and position 4 prime. Similarly, camphorol has hydroxyl group at position 3, 5, 7, and position 4 prime. Now, because these 2 compounds have hydroxyl group at position 3, they are called flavonol, while the remaining 4, litoline, neurorthocaptine, scotylarine, and isoscotylarine, are called flavone because they also contain 4 hydroxyl group, but there's no hydroxyl group at position 3, and therefore they do not belong to flavonol class of compound, but they are flavones. One important thing about this compound is they all have hydroxyl group at position 7 and also at position 4 prime. The remaining 2 hydroxyl group are placed in different position on the backbone of flavone moiety. In general, they also have at position 5 prime and 6 prime, it is unsubstituted, which means there is hydrogen at those points, but the remaining are all either hydroxyl group or hydrogen group. So in these studies, we have 6 compounds which have the same molecular formula and 4 different hydroxyl groups, but at different positions. 2 of these compounds are flavonol, and the remaining 4 are flavones. The objective of this research work is to carry out theoretical study in order to determine the molecular geometries of these 6 tetrahydroxyflavone molecules, and also to calculate the infrared vibrational wave number and simulate the vibrational spectrum of these important molecules, and also to determine the electronic properties of these important molecules, and to calculate global reactivity descriptors and generate molecular electrostatic potentials of this important molecule. And then the last is, of course, to carry out analysis on the binding and the oxidant activities of these molecules by studying the interaction of the molecules with human peroxyridosine protein through molecular docking simulation. For the computational method, Gaussian 03 program package was used for molecular geometry optimization, infrared frequency calculation, and also the electronic properties UV visible calculation. And the computational were performed using density functional theory method and B3 LYP level of theory with the basis set 6311 plus G star star was used for all the calculation. The optimized structural parameters were used for frequency calculation, and the minimum energy structures were found to have no imaginary frequency. For the UV visible calculation, TD-ADFT method was used in using methanol as a solvent, and also Vedavo program was used to calculate the potential energy distribution. This is purely for the assignment of the vibrational wave numbers, and this is complemented with the Gaussian view program to visualize the vibrational modes, just to support and confirm the assignment that is being calculated using Vedavo program. The 3D plots of the frontier molecular orbiters such as HUMO, LUMO, and also molecular electrostatic potential surface were all generated from the Gaussian check files obtained from frequency calculation. The molecular docking investigation was done using the Autodoc package, simulation package. Why do we use density functional theory method? Is because this method has been successfully used for the calculation of the structural parameters, spectral properties, vibrational wave numbers, and electronic properties of different organic compounds. Some of the examples are given here, which is published in computational and theoretical chemistry, that is the study of tetraphenyl ammonium and its derivative. Similarly, we have used the same method on cafetanol and acetophenol drugs, which are well-known analgesic drugs. And we also use it to study tetrafluoroacetophenone using density functional theory method. Pyrrole carboxylaldehyde, the 3 isomers of that were also successfully studied using DFT method. We also have studied tramadol using this density functional theory method. 5-piravir and the structural analogs were also successfully studied and published in different scientific journals. TCNQ and its fluorine and tetrafluoro analogs were also successfully studied using DFT method. We also have used that for diphenyl and diphenylcarbazone and also acetanilide. So in general, our studies have shown that DFT method have given accurate and reliable descriptions of the molecular geometry, vibrational frequency, and electronic properties of organic compounds. Therefore, we found it very suitable to use for the analysis and study of the flavones and flavonols. This slide shows the optimized structures of the flavones and the flavonols that were studied in this particular research work. There are different conformers, but the minimum energy conformers are presented here, and we compare the relative energy, because these molecules they all have the same molecular formula with the same number of functional group but at different position. And in general, we found that all the three rings, that is the two phenyl rings A and B, and the aromatic paranone rings are all planar for all the molecules. And Fercetin, it's and camphophyrol have planar configuration. These are the flavones that have a planar configuration. I mean, all the three rings are in the same plane as far as planarity is concerned. But for the remaining luteolin, narotocaptine, scotylarine, isoscotylarine, they all have a distorted configuration. That is, the three rings are not in the same plane. And we discovered that the flavonol, camphophyrol, has the lowest energy, which is 0.0 kilocalorie per mole relative to the remaining ones. And these are the relative energies of different compounds, which means that the position of the functional group has effect on the stability and the minimum energy structures of these particular molecules. This is the overall presentation of the bond length of different units in the molecules. And these bond lengths are compared with the flavone. So we want to see the effect of substitution on the structural parameters. And we discover that the carbonyl bond length decreases on substitution. For example, unsubstituted flavone has the CO bond is 1.227, but it decreases by just little decrease, which is less than 0.04. And each molecules that have, for example here, that have hydroxyl group adjacent to the carbonyl group have the orientation such that there is a intermolecular hydrogen bond between the hydrogen of the hydroxyl group and the oxygen of the carbonyl group. The same goes with all of them. The minimum energy structure have this configuration. Now, when you look at as I mentioned earlier, all the rings are planar. For example, you look at ring A, ring B, ring C. For all the molecules, including unsubstituted flavone, they are all 120 degree. The average bond angle for the rings, ring A, B, and C, are all overall 120, which confirm that they are all planar. But when we try to look at this dihedral angle, that is the one connecting the phenyl group to the two fused ring, we look at this orientation. We rotate this angle 0, 1, 1 prime, 2 prime. The angle is a bit distorted when you look at the unsubstituted flavone, luteolin, norotocaptine, scotylarine, isoscotylarine. But in the case of flavonols, that is the fercetin and camphophyrol, this angle here 0, this dihedral angle is 0, and also this dihedral angle is 0, which confirms that this molecules has complete polarity as far as the complete structure is concerned. The graph here shows the UV visible spectrum that is simulated using TDA-DFT method, and we can see that these are the UV visible spectrum of the molecules. We can see that the lambda max has shifted. For example, this is flavone that is unsubstituted without the any hydroxyl functional group attached to it. When you compare that to the remaining ones, it leads to what we call longer substitution of the central leads to longer wavelength. But the two flavonols, that is those that have the hydroxyl group at position 3, seems to have the highest wavelength. So the position and the substitution leads to a change in the UV spectrums of the molecule. Now we look at the relative energy and the dipole moment. We've discussed about relative energy because we already presented that the camphiferol has the lowest energy, so the energy is 0 here, and then the other ones have higher energy, more as far as when compared with camphiferol. Camphiferol has the minimum energy structure. The dipole moment of the flavonols, that is the camphiferol and festine, are lower than those of the remaining flavones and also less than the unsubstituted flavone. So in general, this position of the hydroxyl functional group affect the not only the energy of the molecules, but also it affects the dipole moments. And when you compare with the unsubstituted, it also leads to a change in dipole moment because of a substitution. But there's no trend as far as these two properties are concerned. The electronic properties, that is frontier molecular orbitals, were generated, and the LUMO, HUMO energies were used to calculate global reactivities such as ionizing potential, electron affinity, electronegativity, chemical hardness, chemical potential, and electrophilicity. And these are all presented here, and all are compared with the flavone, and these are the 6 substituted molecules that were studies in this particular research work. In general, there is no significant difference in the electronic properties of the study molecules, but of course we can see that the substitution leads to the lowering of ionization potential. This is the substituted, unsubstituted flavone, but substitution leads to the lowering of ionization potential, or also it leads to the lowering of the frontier energy gap, which has to do with the stability of the molecule. And then flavonols, the ones with the hydroxyl group on position 3, have the lowest energy gap, and unsubstituted flavone has the highest ionization potential, electronegativity, and chemical hardness. The figure here shows the 3D plots of the frontier molecular orbiter generated from the checkpoint file of the frequency calculation. We have the HUMO and then the LUMO on this side. They have all, in the case of litoline, the LUMO are spread across the molecules. Also, the same thing was observed for the noractocaptine, but in the case of scutelarine and isoscutelarine, the phenyl group attached to the fuse ring are not involved in molecular orbital spread. But when you look at LUMO have the same trend where all the orbitals are spread across the molecule. That is, it covers almost every part of the molecules. The molecular electrostatic potential energy surface, which is also generated from the checkpoint file, give us information about the possible interaction sites of the molecule. This has variation of charge density. For example, we have the red region, which indicate negatively charged region, which is prone to electrophilic attack. We have the blue region, which is electron deficient and is prone to nucleophilic attack. And of course, this is positively charged. And then we have the slightly electron region, which is prone to molecular interaction. And also we have the green color, which represents zero electrostatic potential. And when you look at this, the red region, which is electron region, is concentrated around the carbonyl oxygen and also oxygen of the hydroxyl group, while the blue region, which is prone to nucleophilic attack, are all around the hydrogen of the hydroxyl group. So if you look at this, these molecules have almost the same or similar electrostatic potential arrangement, which reflect the positions of the hydroxyl group within the molecules. The vibrational IR of the molecules were calculated using by frequency calculation. And these molecules, because they have the same molecular formula, they have the same number of atoms, and therefore they generate, we have 636 atoms and 36 atoms. Therefore it generated 102 vibrational modes that are all IR active, and all the vibrational modes are active. And when you look at the region, hydroxyl region, they have different patterns as far as the molecules are concerned. The arrangements are the patterns of the vibrational IR vibrational mode for all the molecules are different. But of course, we carry out the assignment of the vibrational molecules using VEDA 4 program. These details will be provided hopefully when the paper will be published. The last part is the molecular docking, where the free binding energies, hydrogen bonding, and the number of closet residues to the dock flavones and flavonols into the binding site of human peroxyrodosine 5 is being determined. And the results are presented here. We have the flavone, the 4 flavones, luteolin, noracaptine, and isoquetilerine, and then we have scutelerine. All give negative binding energy, including the flavonols. So the selected flavones, all of them fit well into the binding site of the protein, and they form a stable confluence with the amino acid. And the binding energy ranges from minus 5.53 being the lowest, that is the isoquetilerine, to the highest value of minus 6.7, which is for the luteolin. But it is important to know that the luteolin has the highest number of interactions. We have 10 for luteolin, and then 8, and then it decreases to 7. And for flavonols is 6 and 8. So the free binding energies of the stable molecules vary slightly relative to the most stable one, which is luteolin. And then you have the variation of about less than 1.3 kilocalorie per mole for other molecules. Now this gives the 2D and 3D interactions of the luteolin, which gives the highest number of binding sites. And you have, these are different hydrogen bonding and the binding sites. We have the 2D and then 3D representation of the result. Similarly, this goes for noracaptine, and also we have for the isoquetilerine. This all indicates gives the 3-dimension and 2D interactions of the molecules, the studied molecules, with the human peroxyrodosine 5 protein. In general, what we can get from this is the fact that the theoretical calculation of the structural and vibrational investigation of flavones and flavonols are successfully performed using quantum chemical calculations. The position of functional group do affect the geometry of the molecules. For example, we found that the flavonols are nonlinear, while flavones are non-planar, while the flavonols are completely planar. That is, all the 3 rings are in the same plane. And we've seen that substitution lead to change in dipole moment, with flavonols having the lowest dipole moment. And we also see in the case of UV visible spectrum, the substitution leads to biochromic shift, which means that there is a shift to a longer wavelength on the substitution. But of course, for different flavones and flavonols, generally flavonols have the highest shift compared to the flavones. The molecular orbital, frontier molecular orbital global reactivity descriptors were all analyzed, and there is little or no change in these particular properties. And for the molecular docking, the flavones and flavonols fit well into the binding site of the human peroxyrhodazine 5, and they form stable complex with amino acid of free binding energies, which was found to be in the ranges of minus 5.53 to minus 6.74, of course, for the litoline. And this shows that these molecules are, the negative value shows that the complex are thermodynamically stable. With this, I come to the end of the presentation, and of course, if there is any questions, we'll be available to answer your question. Thank you very much for the time and the audience.